Section 5.5, Alternating Series. This is for all from OpenStax Calculus Volume 2, so please, at the bottom of every page is a link. Go to that link and check out the textbook, because these videos are meant to supplement those. They go together very well, ideally. So, let's go ahead and get started. A series whose terms alternate, that is where the name of this comes from, alternate between positive and negative values is an alternating series. For example, the series from 1 to infinity of negative 1/2 to the n is negative 1/2, positive 1/4, minus 1/8, plus 1/16, minus 1/32, etc. It swaps between positive and negative at each term. And another example, the sum from 1 to infinity of negative 1 to the n plus 1 over n is positive 1, negative 1/2, positive 1/3, minus 1/4, etc. Both of these are alternating because they alternate between positive and negative values. So whenever you have an alternating series, we have this test right here. The alternating series test, I will often write it as the AST. An alternating series of the form, the sum from 1 to infinity of negative 1 to the n plus 1 times some sequence Bn. We will define what that is depending on the problem. Or sum from 1 to infinity of negative 1 to the n, Bn. That series will converge if two things occur. If each term is greater than or equal to 0, and this is decreasing. If b of n plus 1, that term, is less than or equal to b of n for all n. If the entire sequence is decreasing, it's all greater than 0, and the limit of that defining sequence is 0. And we call this the alternating series test. So let's look at a couple of examples. 45. Determine whether the series converges or diverges. Alright, well, for this series, the sum from 1 to infinity of negative 1 to the n plus 1 over n squared, the defining sequence is 1 over n squared. Okay, fair enough. So in that case, we need to first determine whether it is decreasing or not. I believe it is, if you just think about it. 1, 1/2, 1/4, or 1, 1/4, 1/9, because they're perfect squares. Those appear to be decreasing, so I'm going to work that out in general. All right, bn plus 1 is 1 over n plus 1 squared. So that is 1 over n squared plus 2n plus 1. That is definitely less than or equal to 1 over n squared. So bn plus 1 is less than or equal to bn for all n greater than or equal to 1. Now, are those always positive as well? Yes, because we're squaring. All right, so in that case, that is condition A. Condition B is that the limit of 1 over n squared, 1 over n squared is 0, and it in fact is. Because both of those apply, okay, by the AST, the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n squared converges. Okay. Because both those conditions apply, we can say that it converges. Next example, we have the sum from 1 to infinity of negative 1 to the n plus 1 times n over n plus 1. First condition, bn is n over n plus 1. Is that decreasing? All right, so bn plus 1 is n plus 1 over n plus 2. Is that, in fact, less? So just for some intuition here, this would be 1 for bn, that would be 1/2, 2/3, 3/4. For each of these terms, that would be 2/3, 3/4. All and we have 4/5. And it appears to be term by term that it decreases. Okay, that's probably sufficient for the moment. If I could show it in general, that'd be better. We're going to go ahead and say, yes, it decreases. All right, is that sequence n over n plus 1? What is the limit? The limit is 1. That approaches 1, which means the AST does not apply. The AST, alternating series test, does not apply. So it is inconclusive. So that does not tell us whether this converges or diverges. So let's attempt at another test. We could go with one of the limit comparison tests. I don't think this is going to be comparable to a p-series or geometric. However, the divergence test says that if our sequence defining our series goes to anything other than 0, that it diverges. Because Bn goes to 1, the sum from n equals 1 to infinity of -1 to the n plus 1 times n over n plus 1 diverges. Because the sequence defining that does not go to 1, or it does not go to 0, this, in fact, diverges. Sorry, I want to make my writing legible. Fault, I suppose. Go to this website right here to check out this amazing textbook. Please do that before it's all said and done. Pause the video and go look it up now. Download a copy while you're watching. All right, 47. We have the sum from 1 to infinity of -1 to the n plus 1 times n divided by 2 to the n. Let's first determine if this is decreasing. All right, so b to the n, or b sub n, is n over 2 to the n. All right, now b sub n plus 1 is n plus 1 over 2 to the n plus 1. I would like to start by assuming that it is going to be decreasing and see if we can kind of get some intuition here. So this would be, we want n plus 1 over 2 to the n plus 1 to be less than or equal to n over 2 to the n. That is true if and only if 2 to the n plus 2 to the n, I'm multiplying that across, and because all these terms are going to be positive, they're all greater than or equal to 1, the n's are, and 2 to the whatever power, 2 to any power is always positive, I can do this without worrying about the sign there. That is 2 to the n plus 1 times n. All right. Let's see what I can do. I can subtract. Let's rewrite this. 2 times 2 to the n times n is less than n times 2 to the n. Let's keep it in the same order. 2 to the n times 2 to the n. If I subtract a 2 to the n times n from both sides, that'll be 2 to the n is less than or equal to 2. That'd be one of those. Hold on. If I subtract that, that'd be one of those. That'd be 2 to the n times n. There we go. Which is true if and only if n is greater than or equal to 1, which n is definitely greater than or equal to 1 for all of these circumstances. So ideally, I would now work backwards to show that b n plus 1 is less than or equal to b n. Okay, if all the terms are greater than 0, it is decreasing, so this is all part A. Part B, does n over 2 to the n, okay, is that limit in fact going to be 0? Now let's first apply L'Hopital's rule. Actually, let's write that clearer. Let's put limit over here. And this is because of L'Hopital's rule. That would be 1 over natural log 2 times 2 to the n, which will most certainly go to 0. So in this case, by the alternating series test, sum from 1 to infinity of negative 1 to the n plus 1 n over 2 to the n converges. And there we have it. Okay, we now have a definition, absolute convergence. A series, the sum from 1 to infinity of a sub n, exhibits absolute convergence if the absolute value, the sum from 1 to infinity of the absolute value of that sequence converges. The series exhibits conditional convergence if the sum itself is convergent, but the sum of the absolute values diverges. All right, now, a very important theorem that we are going to use several times here is absolute convergence implies convergence. Absolute convergence implies convergence. All right, so we want to determine whether these series converge absolutely, conditionally, or if they diverge. So let's first take a look at this one. So the sum from 1 to infinity of negative 1 to the n plus 1 over 3n plus 1. All right, well, let's first consider the absolute value. Okay, so let's first consider the sum from 1 to infinity of the absolute value of that is 1 over 3n plus 1. Now, that appears we might be able to compare it, that to 1 over n. Okay, so let's do a limit comparison test. Okay, the limit as n goes to infinity of 1 over 3n plus 1 divided by 1 over n. That is going to be, once we rearrange that, 1/3. Okay, by the limit comparison test, that goes to something that is not 0, so they both either converge or diverge. So this sum diverges. Okay. By the limit comparison test, this diverges. Okay, now that was for the absolute value of that. So since that diverges, we could possibly have conditional convergence. Now let's determine from the sum n equals 1, negative 1 to the n plus 1 over 3n plus 1. For this one, this is an alternating series. So let's suppose and look into if the alternating series test applies. Well, it appears that the defining sequence, bn equals 1 over 3n plus 1, goes to 0. Okay, that is part B. Now, does bn decrease? So that would be 1 over 3n plus 1 plus 1. That would mean that is less than or equal to 1 over 3n plus 1. Well, that would be 1 over 3n plus 4 and because the term on the denominator on the left is bigger, this is going to be true. So this decreases. It decreases. That defining sequence goes to 0. All right, therefore, by the alternating series test, sum from 1 to infinity of negative 1 to the n plus 1 over 3n plus 1 converges. Okay, now let's revisit. This first portion, in this first portion, we looked at the absolute value of this. Okay, this was us looking at the absolute value of a sub n. Okay, that was the sum, the absolute value of a sub n. That diverged by our limit comparison test. Okay, but without the absolute values, the alternating series test tells us that it converges. So that means this converges conditionally. That is, okay, the sum of n equals 1 to infinity of negative 1 to the n plus 1 over 3n plus 1 converges conditionally. Which is what we were after. Determine if it converges absolutely, conditionally, or diverges. Or 49. Determine whether this series converges absolutely, conditionally, or diverges. So let's first consider the absolute value. Okay, so the sum n equals 1 to infinity of the absolute value of cosine n over n squared. Okay. Well, this is going to be less than or equal to sum from 1 to infinity of 1 over n squared. This converges. Okay, so that is sum from 1 to infinity of the absolute value of cosine n over n squared converges. All right, so by definition then, this converges absolutely. Okay, we only have to look into conditional convergence if the absolute value does not converge, if it diverges. So therefore, sum from 1 to infinity of cosine n over n squared converges absolutely. Number 50, same question. First thing we want to do is consider the sum of the absolute value of negative 1 to the n plus 1 n over 2n cubed plus 1. Now, because n is positive, this is just equal to the sum from 1 to infinity of n over 2n cubed plus 1. Now, this is less than or equal to, term for term, n over n cubed, which is the sum n equals 1 over n squared. That converges. Okay, this sequence, or this series of the absolute value of negative 1 to the n plus 1 n over 2n cubed. Oh, actually, let's first discuss this, because 1 over n squared converges. Okay, because that converges. The sum, the absolute value of negative 1 to the n plus 1 n over 2n cubed plus 1 converges. And the sum from 1 to infinity of negative 1 to the n plus 1 n over 2n cubed plus 1 converges absolutely. And that is the last section, or the last question in this section. Right, so hopefully we can have a good grasp on the alternating series test whenever that comes up. Notice whenever it's going positive, negative, or, as you hopefully have picked up, every time we have a negative 1 to some power, alternating series test is good to go. That's it.